Okay, and then further to that, right, the second pillar of innovation is to look at cloudification. So when you look at the terminologies used, right, in terms of RAN, virtual RAN, and Open RAN, the key difference between virtual RAN and Open RAN is that Open RAN can actually run the radio network functions like the DU and CU on other vendors' cloud system, which are not vertically integrated by a single vendor. Okay, so single vendor radio access network, when you support virtualization, cloudification, is called a virtual RAN. But then to be able to really deploy the virtual DUs, virtual CUs, the rigs, right, on a cloud platform from another vendor, and then to be able to manage the clouds, orchestrate the cloud resources with a service management orchestrator, this is what we call the open cloudification, separating the software and the hardware. Now, further to that, the third pillar of innovation is to look at open intelligence, right? This is where the service management orchestration, the rigs, right, basically the near real-time rig and the non-real-time rig, are basically looking at different timescales of optimization using artificial intelligence, machine learning, would actually play a role here, right? The single vendor RAN solutions today has already been utilizing AI ML for quite some time for radio networks optimization, right? Be it traffic steering, load balancing, mobility robustness optimization, right? Of different timescales. So Open RAN is to basically look at how can we try to support applications, right? The radio resource management optimization, customer experiences, analytics applications, right? That the customers, the operators, the entire ecosystems of application developer will be able to develop applications on top of these platforms using standardized APIs and measurements, right? Controls coming with this standardized APIs, right? So that's the third pillar of innovation. Again, utilizing artificial intelligence, machine learning to enable network automation, orchestration management. The other aspects of it as well is a very heavily research topic at the moment, right? For standardization is what we call the intent-based management. So today, radio access network is very complex to really manage, optimize, troubleshoot. And even if the operators wanted to be able to say, well, I want to be able to sell slice as a service, right, to their customers. As lots of engineers will need to be able to look at how we can try to configure slice as a service. Intent-based management is really intended to simplify the configuration just so that operators can actually use it in a friendly way and say, by the way, I want this network slice to support this SLAs, right? And then you will be able to, the system, right, will basically provide a translator to translate something that's actually human consumable to machine language, right? Just so that the underlying Open RAN system can actually be orchestrated, configured, and managed in a way to fulfill the human language requirements, right? Coming from, human beings, right? Like yourself and myself. Okay, so these are the three key pillars of innovation. Now moving on to the benefits, challenges, and industry actions, right? For Open RAN. And obviously, Open RAN doesn't come for free, right? But we look at the benefits first, right? What does it actually bring to the operators? The first thing would be supply chain diversification. This is very clear. I mean, so we have very, very good single vendor radio access network supplies today, reliable, very, I mean, they really spend their time in terms of engineering the radio access network, right, and optimize it really well. However, there are only a handful of suppliers out there in the markets. And then I think the vendors themselves, they're trying to do as much as they can as well to be able to meet the needs of different requirements coming from the telco use cases for today, and as well as use cases for tomorrow. For example, we speak about metaverse, we speak about industry IoT, industry 4.0 using 5G connectivity. So I think the time has arrived that basically the industry would need to be able to look at if there's going to be open interfaces with well-defined specifications, right, in terms of implementation that support multi-vendor interoperability for the radio access network, then this could open up, right, the supply chain so that the components by themselves can actually be each selected, and this would actually result in a richer solution ecosystem like vendor A, vendor B can actually get together and say, maybe we can try to create a solution together for the industry IoT use case, for maybe aircraft maintenance, right? And this would as well spur new innovation models. Now with the entire industry coming together, it's beyond a few companies, and you got application developers that will come up with all kind of ideas, right? And say, these are the visibility that we need, right? In a smart factory environment, in a private network. I mean, the whole concept and the whole innovation will just proliferate into the industry when you start to look at unlocking some of this intelligence right within the radio access network. We've actually spoken to a few private network operators. Open RAN is definitely an avenue for them to unlock revenue opportunities for the current telcos and for some of the service providers. If you look at Germany, for example, some of the OT players have already sort of made announcements, right, to make use of the spectrum which is dedicated for private networks, and starting to experiment Open RAN on how this can potentially provide the connectivity for their use cases, right, for smart manufacturing, and as well as simplified management, optimization, lower total cost of ownership. Now, when we start to look at challenges, multi-vendor interoperability is definitely one of the key ones. Now the question is that you used to have a single vendor providing everything. It's like when you buy a fridge, right? You can go to LG, Samsung, or just anyone who provided the fridge and say the fridge is not working after 2 years, right? The warranty is for 5 years. Can you fix it for me? Can you replace it? Now, when the system is actually consisting of a multi-vendor solution, who do you actually go to? How do you make sure that the condenser from one company is actually working well with the condenser or compressor from another company? Those sort of things, right? I think you need to make sure that the test and integration aspects from an end-to-end perspective for the entire life cycle, right? Starting from the chip design all the way to deployments, operations, they really have to be thought out. There were some discussions about the speed and cost of evolution. You got the system from multiple vendors. If you want to be able to perform an upgrade, right? Like for example, to support 3GPP release 16 or 17 features, each of the components got to be tested and the entire system got to be tested. What will be the impact to the speed and cost of evolution? Security is another one, right? You got more vendors in the mix right now. How do you look at security? Finger pointing is a major concern for many of the operators, right? Now you basically would have single vendor providing the RAN, but now with Open RAN, there are multiple vendors. If there are issues within the radio access network, how do you identify them? How do you eliminate finger pointing? I said, let's try to solve this problem together. And the last point is around the true TCO, the CapEx and OpEx of Open RAN, right? Is it really saving the operators costs with all these challenges that we're presenting here? And there are others, right, challenges, obviously. From an industry actions perspective, it's over the past few years, and the industry, including Keysight as one of a major driver, we'll be working very hard on standards, right? To support multi-vendor interoperability, standards is fundamental so that the RU, DU, the RIC, the near real-time RIC, non-real-time RIC, accept RFs, right? The cloud, the XOR, SMO, can all talk to each other, right? Based on a common set of language. Now you design the technical specifications, right? For all the interfaces to be open. You want to be as well, making sure that we design test specifications, right? So they can test it for conformance to the specs, the interoperability test, end-to-end test, performance and security test, really important. And we talked about how we can try to accelerate the lab to field, which basically involve, right, implementing a continuous integration, continuous deployment, continuous testing digital pipeline to accelerate lab to field, and ensuring that you utilize, right, or leverage AI/ML to enable network automation to simplify operations, which is particularly important in a multi-vendor setup. From a security perspective, we look at a 360-degree DevSecOps approach in terms of how do we constantly simulate attacks, like DOS attacks, right, on different interfaces of the Open RAN network. How do we make sure that we can actually improvise or implement a detection mechanism and a defense, right, against attacks, right? All those have to be validated for all the components and for the entire system. And when there are issues, right, basically appearing in the lab, in the field, in operations, how do we eliminate finger pointing? You need end-to-end observability, right? Basically the interface, the physical and the virtual domains. And the last part is really important recently because obviously we know that prices has really went up, right? Inflation, just about everything. Energy, right, is a scarce resource. So recently we've been getting a lot of questions about, what is a true TCO apart from obviously the test integration costs, vendor management and stuff like that. Energy efficiency came up to be a new plane for differentiation, right? We have actually seen some announcements from some of the operators in Europe that because of the rising energy costs, is starting to impact their profitability in a significant way. One of the other operator basically said that it may slow down 5G deployments because of the rising energy costs. And these are real problems that we're going to tackle today and not wait until 6G, right, in terms of energy efficiency, because it basically adds up, right, to a big portion of the operator's operating expense. And that cost is continuing to rise. From the Open RAN deployment perspective, I think we have actually seen many announcements. On this slide is basically a snapshot of what has been, in works in the industry and then in progress. So I picked on one case study that we've actually looked at, that Vodafone basically got together a set of partners, right, that includes Samsung, Wind River, Dell, Intel, Keysight. Every company, basically, leaders in our own field. Keysight, we focus on test and measurements. And then to look at building Europe's first commercial Open RAN network. I'll share more details in terms of, and this is public information, right? I'll share more details in terms of, it's not related to specifics of this public announcement, but on the steps, right, to really accelerate Open RAN trials and deployments, okay, as a case study. So from the ORAN Alliance perspective, right, as I mentioned, is the only standards development organization in the industry today globally that looks at developing, Open RAN specs and standards for this technology. And I just want to give a very brief introduction of the different working groups responsible for different parts of Open RAN at a very high level. So you have working group 1, basically that looks at the use case architecture for the entire Open RAN. What does Open RAN needs to support, right? Because it goes back to the use case and you define the architecture. Working group 2 focuses on the non-real-time rig. So this is for optimization, right, larger than, I believe, 1 second. That you can really make use of machine learning, artificial intelligence, and implement policies for the entire ORAN network. And it looks at A1, which is the interface between the non-real-time rig, near real-time rig, and the R1 interface that basically enables multi-vendor RAPs. Working group 3, near real-time rig, which is this component here, supports multi-vendor accepts, and the E2 interface between the near real-time rig and the E2 nodes. Working group 4 focuses on the Fronthaul. This is actually the Fronthaul is the most matured part of Open RAN at the moment, right? The rest of the components, they are catching up really fast. But in terms of commercial deployments hitting the market today is Open Fronthaul, basically supporting multi-vendors, radio units, and distributed units. Working group 5 focuses on interoperability, right, over the X2 interface, XN between the base stations, between the CUDUs, F1, E1. Working group 6, supporting multi-vendor OCloud, management orchestration of the OCloud interface, and as well as enabling the OCloud to use different vendors, accelerators, for example. Working group 10 looks at the entire SMO, the orchestration and management over the O1 interface for all the managed functions. And there's actually other common working groups across, right, the entire ORAN architecture. Working group 7, white box implementation. Working group 8, reference stack. Working group 11, security from the entire ORAN Alliance per component, per interface. And for the entire ORAN, test integration focus group, right, test plan strategy for the entire Open RAN testing. ORAN Alliance has recently formed a research group focusing on 6G, right? So no standards yet, but looking at researchers in terms of what would 6G, use cases and requirements, right? What kind of implications would it have, right, on Open RAN? And then there are additional groups that does the planning, the roadmap planning, MVPC, industry engagement, standards development, processes, and open source. all managed by a technical steering community, right? So this is ORAN Alliance in a nutshell. And then we have 31 operators, members today, and 300 plus companies from different parts of the ecosystem. Okay, so now that we talk about Open RAN, I wanted to go through some of the case studies with you in terms of how we basically have been working with our partners and our collaborators to accelerate Open RAN deployments. There are 9 blocks here, 9 use cases that I wanted to go through the team. But then because the time in this meeting is limited, so I may not have time to go through all of them. I've selected a few key areas that I wanted to share with the team. Right, so the first one is in terms of ORAN, conformance, IoT end-to-end, certification and badging. Right, so we look at the compliance to the specifications, interoperability test, and the end-to-end test. The other use cases includes massive MIMO optimization. How do we look at a realistic testing environment in the lab? Because massive MIMO, multi-user MIMO has always been tested in the field, right? Because in the lab, the environment is very static, right? I think for those of you who are basically have a good understanding of massive MIMO, is that in the lab testing, you will not be able to move the beams, you got limited subscribers, testing the network is not really testing what massive MIMO, multi-user MIMO is designed to work. So this is the one whereby I may not be able to share all the details in this meeting because of limited time, but we'll discuss them later. We plan to share more information about cybersecurity, live to lab testing, right? So testing your lab setup, right? The device under test in your lab environment with real world conditions simulated in the lab, right? So we bring the field conditions back to the lab to perform realistic testing. This would accelerate the lab to live deployments, right? If you're just testing based on ideal conditions, you will have no chance, right, to deploy whatever you test in the lab into the field and expect it to work. And to test in the field is always needing a lot more time in terms of optimization and troubleshooting. We'll speak about the visibility and troubleshooting aspects. Remember, we talked about finger pointing. How do we eliminate finger pointing, right? This is essential to deploy Open RAN. We test as much as we can in the lab. There's always going to be issues, right? Basically creeping out to the field. How do you support a mechanism that we can try to get visibility and then to be able to use analytics, right, to isolate the root cause and to eliminate finger pointing? Infrastructure, cloud transport testing, I would not have time to cover in this meeting. Energy savings efficiency, we'll leave it to the next meeting, and I'll speak a little bit about AI ML optimization and zero touch auto automation if we have time. Okay, so in terms of the testing methodology, there are 3 stages, right, of what we call the testing methodology recommended, right, and obviously specified in ORAN Alliance. The first one is the conformance testing and subsystem testing. This basically involves testing every component in isolation. So the blue boxes you're seeing here, these are the device under test. So we mentioned that if we want the open Fronthaul to be robustly tested, that's the interface between the DU and the radio units, then you got to make sure that every single component is actually tested and validated to comply to the standards that ORAN Alliance has written for Fronthaul. So you need to test each of the component in isolation in a wraparound approach. So what you're seeing here, this is the standardized test setup in ORAN Alliance, whereby you got the radio units. On the radio interface, you're connected to the signal analyzer, signal generator, that's radio. And then you'll be connecting to a ODU emulator over the Ethernet Fronthaul interface together with an SMO emulator for management plane. Similarly, for the DU, it's going to be a wraparound test whereby the device under test is the ODU. And then we would emulate the radio units, right? The red color boxes, these are Keysight test tools. And within the radio unit emulator, we emulate UEs, right, to be testing the ODU. And the back end of the ODU is connected to the OCU, the core network, and the SMO emulator. So in this case, you basically can perform a very detailed verification of the nuts and bolts of each of the DUT. And in cases whereby we need to be able to perform machine learning training, right, for the applications like the XApp and RApps, it can be done in a very containerized and high performance fashion without interference from another device under test, for example. So once we get past the conformance test as a single device under test, right? You make sure that the individual components are well tested. You move on to start to put that putting together two devices under test, which is what we call interoperability testing. In this case, the radio unit and DU, this is used as example. We basically add channel models, right, to the radio unit, the interface between the radio unit and the EUE, and as well as the impairments to the network between the DU and RU. And then again, this is a wraparound framework, right? The red color boxes, basically these are test tools emulating the UEs, the CU, the core and SMO emulator to make sure that the DU and radio units, they're tested in isolation as a pair. Now, when each of the components and pairs of components that are tested, we move them to the end-to-end test. End-to-end test can be performed either in the lab and in the field, and the entire deployment blueprint is a system under test. So you can test using the UE emulator and the test UE in the field with the core network emulator, obviously with application traffic to drive the entire system, right, for end-to-end testing. Within ORAN Alliance has defined a mechanism for what we call certification. It's like when we want to drive a car on the road, we need to go to the driving centers to take our driving test. So the driving centers, in the case of ORAN Alliance, we call them OTIC, Open Testing and Integration Center. These are the places whereby I can bring my ORAN solutions to this lab. And if I pass all the conformance test cases, which are needed for certification, I would apply for a certificate to be awarded to my specific device under test, right? So this basically gives a assurance, right, to the consumers or the operators that when a vendor bring their solution to them, look, I got a certificate from this OTIC, right? They have actually passed all these tests. This is, building confidence, right, for them. And badging for IoT would apply for the Fronthaul interface, interoperability, and then there's a badging from end-to-end perspective as well. So this is one of the mechanisms that's actually been put in place to look at how we can try to perform a basic level of testing that allow the operators to believe that the equipment that's actually been brought to them is compliant to ORAN specifications in various forms. So from a conformance and certification perspective, we are very happy that in June this year, ORAN Alliance has awarded 2 ORAN certificates to 2 radio units, and obviously their companies will basically design and manufacture these radio units. This is one that requires very extensive testing. So the conformance test specs from Working Group 4, the Fronthaul group, has been used for certification testing. It basically requires very comprehensive testing of the control user synchronization management plane, right? There are 31 test cases involved, and the testing was actually performed repeated again and again, and the results were validated thoroughly. Again, this is all the control user synchronization management plane, and expertise with in-depth understanding of the Fronthaul technical test specification expertise were basically required to perform this verification. So there were test automation involved, reporting obviously of the results, and the conformance test and certification test will work for frequency range 1, frequency range 2 millimeter wave. The specific certification test that's actually been performed was actually based on frequency range 1, but the certification mechanism and the conformance test specs will be applicable for FDD, TDD, Cat A, Cat B radios, massive MIMO, non-beamforming radios as well, right? So this is a test setup that we just went through. And then in addition to the signal analyzer, signal generator, and as well as the ODU emulator, what's actually necessary is that some of the test cases basically requires impairment to the PTP signal. So the synchronization plane, right, that basically is designed for the Fronthaul. We need to impair them, right, for some of the test cases to be executed. And on top of it, right, you want to be able to deploy solutions, right, to look at the interface and the Fronthaul interface with analytics so you can troubleshoot issues during the test. Okay, so this is the conformance and certification aspects of ORU. Now, when we look at, remember I mentioned that for conformance, interoperability, end-to-end testing, every single component within the ORAN system will need to be tested for conformance, right? not just from a functional perspective, but from a performance perspective as well. So this slide here, basically we looked at, again, the blue color boxes are the device under test. It's a comprehensive set of solutions that basically uses UE emulation to be driving stateful tests from both a functional and performance testing to test the DU, right? So this case, basically the RU is emulated and this is a standalone DU. The backend is basically a CU emulator that we look at testing the ODU in isolation. This is the case whereby we look at testing the ODU, OCU as a pair, right? Some of the setups that we've seen is that some of the vendors provide a combined CU-DU unit. So we don't actually need to emulate the CU, but we can emulate the CU if it's actually a standalone DU. And this is the one that basically looks at testing the OCU in isolation. We emulate the DU and the backend UE. And then the backend is automated by a core emulator with an IMS emulator built in. This is a test setup that we test the near real-time rig, the non-real-time rig, and the applications within the near and non-real-time rig together at SMO. In this case, we emulate the ORU, the E2 nodes, right, which is basically the OCODU and the backend UEs, right? So that it's an entire network that we're emulating to train, accept the RFs, right, with data and to test it with lots of emulated nodes and subscribers. On top here, this is the ORU, ODU, OCU. These are all the device under test. This is called what we call the end-to-end system testing. We test it in the field, in the labs with test UEs, right? And as well as with UE emulator. And if the ORU is basically supporting massive MIMO beamforming, we need to be able to make sure we can test massive MIMO, multi-user MIMO realistically in the lab, which is why we have a massive MIMO intelligent connector that looks at testing the ORU, again, with full mobility support, with the right channel models and conditions in the lab, basically modeled after field conditions. And this is extremely critical, right? And not getting restricted with limited mobility, limited subscribers, which really doesn't exercise the full capabilities of multi-user MIMO, per design within the GNOB. Okay, so now we covered conformance, IoT, end-to-end certification, badging testing. I'd like to move on to the live to lab deployment. This is one that we've actually been spending quite a bit of energy into. So when we first started collaborating with our partners many years ago on Open RAN testing, all the test setups are based on ideal conditions, right? So we know that in real life environment, right? This is a picture, and I wanted to thank Docomo, right, for putting together this picture, which was published in their technical journal quite some time ago. So when we look at deploying the DU and the RU in live networks for macro networks, it's always a distance apart, right? It's not like in the lab, right? You got the DU and RU, you connect using a straight fiber, and the latency is close to zero. There are no packet losses, no jitter. So when you're testing the DU and RU with ideal fronthaul, it's ideal conditions. But in a live environment, operators are deploying the DU and RU, up to 30 kilometers apart. So there's going to be latency, jitter packet losses with switches in between the DU and RU, multiple hops. So within the ORAN Alliance specification from Working Group 4, there's a robust mechanism. It's called the delay management, being designed into the DU and RU. So you can try to handle and take into considerations the varying delay introduced by the DU internal processing, which may increase or decrease, right, depending on the loads of the DU. And every DU is actually designed with limited memory buffer. The radio unit basically have the same processing delay right over here, and the transmission delay, right, from one point to the other point, both in uplink and downlink. This is what we call the delay management. And as you would have imagined, that there's only certain timing windows, right, that the RU will be able to receive a packet, because the RU is not designed to be like a petabyte hard disk, right? It doesn't have lots of storage. So the packets which are sent by the DU to the RU over the fronthaul interface, including the delay internal to the DU and RU, must be within a very short window, right? Because you cannot buffer packets forever. So if it's too early or too late, you drop the packets. If you drop the packets, you'll basically impact customer experiences, obviously, right? So then, fundamentally, this doesn't work. So how do we look at testing this in the lab? We mentioned that if you're basically testing with a straight fiber connecting between the radio unit and the DU, then you will not be able to bring the real-world deployment conditions into the lab, right? Real-world deployments, they are not ideal, right? So to validate this, basically we look at, and by the way, this is a table that has a listing of the different specifications, test specifications within ORAN Alliance for Working Group 4, 5, and Test Integration Focus Group that requires and specified test case for network impairments to be performed to the network when you do your test, right? Just to make sure that the true conformance, interoperability, and performance tests can be performed, right, only with simulated or emulated network impairments introduced to the network under test. And this will obviously be mandatory for certification, right, and badging purposes. So we've actually inserted this transport network emulator, right, impairments over here, this block I'm highlighting here using the laser pointer. So the same test setup, right, as we covered in the earlier slide for conformance, interoperability, and end-to-end testing, we are basically inserting a configurable, precise delay, packet loss, and jitter impairments into the front haul, into the mid haul, into the back haul for all the testing. And this is critically important, and we should do that, right, basically for both the uplink and downlink underlying rates. This is the only way for us to be able to inject impairments, right? Taking impairment profile from the live network, for example, some of the operators actually have 2 hops, right, of switches and routers between the DU and radio unit. And the profile in terms of impairments from the transport network perspective is actually being programmed into the network emulator. And now you can look at testing conformance IoT end-to-end with real-world impairments, right, added to the transport interfaces. So this is really key. I'd like to move on to the end-to-end visibility and troubleshooting. We have actually worked with many operators and obviously many of our vendors, collaborators. Everyone is actually thinking of like, okay, we've actually done the conformance IoT end-to-end testing. Now 2 vendors have gotten certificates, and there are more vendors within the ecosystem that will get awarded certificates and badges from the OTICs, right? The Open Testing and Integration Centers. We spoke about, performing realistic testing in the lab, right? Using field conditions, right? Like for example, the front haul delay, packet loss, and jitter introduced to lab testing conditions. But there's going to be problems, right, that we're going to see in the labs during testing with other vendors in the lab, in the field. How do we try to isolate this? So end of the day, I think there's always, when you test, right, there's always going to be problems, right? And the problems could be because the specifications are still, maturing, right? All the specs will need time to mature. It's only when you test them, you find issues, right, in terms of maybe there are different understanding of the specifications. It's not tight enough in terms of the interpretation. So you got to test it, you find the problems, right? Say, okay, the specs is not clear, right? So we got to enhance the specs, retest it again to make sure that the specs is really tight so that there are no room for ambiguity that will result in interoperability challenges. And then there could be as well suboptimum implementations, right? Because everything takes time to mature, right? Rome is not built in a day. So when you start to look at what we need to do here, you got, in this case, the radio unit, the DU and the CU, the MAC and the core. These are devices under test. And then remember we said that, the UE emulator test UE would actually be testing the entire network. And we deploy a mechanism, right, what we call the air monitor, to monitor the entire carrier of the interface, right? Then we start to look at monitoring the front haul interface as well and analyzing the data. The front haul interface is very complex, right? Basically, the control user plane, they are basically carried over eCPRI packets. And these are frequency domain IQ data from a user plane perspective, which requires demodulation, right? So you can capture the packets, but analyzing the packets of lots of frequency domain IQ data with eCPRI data doesn't really make sense. You really need to be able to go up a level, right, and start to look at, okay, what are the user experience impacts? And is it caused by issues, right, in the radio units over the RF interface? Is that caused by issues, right, in the radio unit, which basically results in problems over the front haul interface? Or is it the DU problem, right, in terms of implementation of the open front haul? Is it a CU problem, a MAC problem? So then you have basically packet brokers and as well as virtualized agents, right, being deployed for visibility purpose across the entire network. So now we get the interface, we get the Fronthaul interface, we get the network interface, everything correlated together to provide end-to-end visibility, right, for all the test setup that includes end-to-end, conformance, interoperability. This is really the key. It's not just about getting the packets, it's about analyzing the data, right, and providing actionable intelligence on top of the data that you can actually help operators and vendors, right, perform troubleshooting very easily. And that's really the key here. Without this, you can test, right, and we need to test, but the root cause identification will be extremely challenging. That's the experience that we have. Okay. Briefly touching on the cybersecurity, as I've mentioned, right? So we know that, so I would like to maybe refer you to this report. I added the link to the webinar slides. Security is a very big topic, right, in Open RAN. So ORAN Alliance has set up a dedicated group. It's called Working Group 11 to look at all aspects of security on a per module, right, per interface, the entire system, because it really expanded the threat surface, right, vulnerabilities because of open disaggregation. There are more vendors getting involved, and then the products are maturing, the standards are maturing. We talked about, attacks, right, even on the cloud. When you got multi-tenancy, right, multi-vendors running on the cloud, if the cloud get attacked, how would different vendors, DU, CU behave, in response to the attack? And there are increased number of suppliers needing to be vetted. Automation by itself would have flaws with machine learning models. There could be applications that potentially could be malicious, right? Stealing your customer data, the integrity of the applications, the data privacy, the data sources, which are basically being used to train the models for machine learning. These challenges are very well summarized in this EU report, right? Basically look at the cybersecurity risks of Open RAN. And I just wanted to emphasize something really important, right? Yeah, the risks are not just being introduced by Open RAN. Many of the security risks exist as well today for single vendor radio access network, but obviously without all the open interfaces, without the multi-vendor aspects. But things like, for example, the machine learning models needing to mature and stuff like that, they will still exist, right? So it's a challenge that we have to solve as an industry, not just from Open RAN, but from a RAN perspective, right, mobile networks perspective, now with 5G and then moving to 6G. Okay, so from our perspective, the solution is really about understanding the device, right? We need to be in a live network serving subscribers. Now we basically emulate the UEs, we emulate the radio units to be testing the entire network, including the rigs and the application. Now we create different kind of attacks, right, to be driving the network. So we basically attack the network when it's actually serving subscribers, right, like yourself and myself with different applications, and simulate lots of DDoS attack, denial of service. We start to look at doing protocol and port vulnerability scanning. We basically generate different patterns, right, for fuzzing tests, right, just attack the network in general at random, which with unexpected inputs, and then attacking the cloud. So basically you got a DE or CU or rig running on the common cloud infrastructure. Now if I can emulate malicious virtual network functions, cloud network functions, and start to look at monopolizing all the resources in terms of computing, networking, and as well as storage in the cloud infrastructure, and staff the resources, right, which are basically made available for the actual network elements, and see how the system behave. So we add everything together again, right? The attacks, the detection, and the defense, right? This is what we're trying to put together in this cyber range testing solution, right? We're very excited about this, right? This is definitely an aspect that needs to be looked at holistically throughout the entire life cycle of Open RAN. So I know I've actually spoke a lot, and I wanted to summarize, right, some of the highlights, to the team, because we're getting close to the end of this technical webinar. I think, without a doubt, right, we're basically all seeing that Open RAN has gained significant momentum. Operators are engaged. Operators are pushing for this revolution. I would say in terms of the strategy of Open RAN, it varies between operators, right? Because it all depends on Open RAN is not about adopting all the openness aspects of Open RAN. So in other words, you do not need to implement the Fronthaul, the mid-haul, the rigs, the accept, the RFs, the SMO, everything at the same time. It's about mapping out the benefits, evaluating what Open RAN can do to support your business model, whether this is public network, private networks, and then select the components, form the consortium, and work on it, right? If you don't explore it, you'll never know. It's really opening up, commercial deployments for 5G globally, both for public networks and private networks. We're starting to see some of the OT players, what we call operational technology players, to adopt Open RAN in terms of testing, right? Experiments to see what Open RAN can do for them for smart manufacturing, connectivity. And now that it's actually preparing for commercial deployments, we're starting to see some significant shift in the ecosystem testing strategy, because the key thing is around multi-vendor interoperability. How do we take that into consideration when we look at conformance interoperability end-to-end, and then from a not just functional perspective, performance perspective, security, energy efficiency, right? We did not manage to cover this in the meeting today because of a lack of time, but hopefully when I get an opportunity to come back again, I can try to go through more information about energy efficiency testing and how energy savings, right, is critical to enable the success of Open RAN. And then some of the new innovative testing approach, like for example, continuous testing supported with test automation, is really required to enable multi-vendor Open RAN deployment scale, right? Really important, which otherwise you will not be able to address the speed and cost of evolution aspects. If one vendor supply a radio unit, you perform a software upgrade, what kind of impacts, right, would it have to the rest of the system or components within the system, right? It requires a very intelligent framework, right, to do the testing, right, and push it through the pipeline. In Keysight, we have combined our expertise, right? I mean, Keysight, we look at across the board in terms of UEs, radio, RF, the RAN, the ORAN, right? Not just Open RAN, but RAN as well. We have years of experience with that and products to support that. Cloud, transport, and AI ML technology domains, right? That basically supports our continuous testing across the entire network lifecycle, from research basically to operations, device to cloud, a full stack, right? Layer 1 to layer 7. So with that, I conclude my presentation for today, and thank you very much for your attention.